Hello, hello. Okay. Is my audio clear? Can anyone confirm in the chat? Am I audible? Cool. So yeah, okay. First of all, this is my first time taking a lecture on an academic platform, so I might be a newbie on some aspects. This lecture is going to be about intro to Biconnectivity. I'm primarily going to speak in English. As for voice breaking, okay, let's see if it persists. Is the voice still breaking? Okay, seems like a local issue then. Alright, so yeah, so the topic is going to be intro to Biconnectivity. Some of the content that I've used has been made by Tanuj for his past video. It was, I think, 2016 or 2017 IPC camp conducted by CodeChef. And yeah, and he also had a blog post on Quora and another platform. As for my introduction, my name is Sidhant. I'm a CS undergrad at NUS, there's this university in Singapore. For my competitive programming experience, I did IOI in 2017 and did ICPC in like these years. Yeah, I'm still a fourth year final year student. So like the topic is Biconnectivity, which is kind of related to articulation points, bridges and everything, and this is going to be a 1 hour session. We are like maybe it gets extended by like 10-15 minutes, but I think we should hopefully wind it up in like 70-75 minutes. Yeah. So yeah, the agenda is going to be this thing, which is we'll first introduce the terminology, which is articulation point. What are articulation points? What are bridges? What are bridge components? What are biconnected components? Then we are going to see how do we implement bridge finding. This is commonly known as Tarjan's algorithm. Some of you might have known about it earlier. Followed by what is bridge tree, the definition of bridge tree, so the terminology is going to be there. Then how do we implement bridge finding, which is Tarjan's algorithm. Then bridge tree. This is the main data structure that we'll talk about. It's created, like you need to know bridge finding algorithm to be able to create this data structure. So we'll have this definition of a bridge tree, some examples. I think the main part will be properties and proofs of the bridge tree, which we'll cover. We'll skim over the implementation. I've already implemented it beforehand. I'll just go through that implementation and tell you guys how it works. And then we'll try to discuss like 3 to 4 problems based on this. 2 of them will be easy, 2 of them will be hard. So the setup is going to be that when I do this, you'll basically see the same set of slides, but I can scribble over them because it's on my tablet. And yeah, and I'll just go back for the touch screen, for the actual, like when we have to actually read through the code. So moving on, let's start. Okay, so what are articulation points and bridges? So like these are the main 2 terms that are essential to biconnectivity whenever you talk about biconnectivity. So firstly, what's a bridge edge? A bridge edge in an undirected graph is an edge whose removal increases the number of connected components of the graph by 1. What it means, like let's try to give an example. Let's say you have this graph. So I'm assuming everyone knows what a graph is, like some vertices and nodes connected. And notice here, one important thing that was written was that it's an undirected graph. That is, the edges are not directed. In this graph, let's label this edge 1, this edge 2, this edge 3, this edge 4, this edge 5, this edge 6, this edge 7. Can anyone tell me what are the bridge edges using the definition? A bridge edge in an undirected graph is an edge whose removal So what's the important part of the definition? Whose removal increases the number of connected components in the graph by 1. Okay. Not sure. So could you see the video just right now when I shared my other screen? Could you see it like 2 minutes back? This thing, can you see it now? Okay, I'm confused. We can see your video now. Yeah, I realized that, but like okay, let's try this. Can you see? Can you see it now? This thing on the top. Okay, you can see the yellow marker, right? You can see the yellow marker. Not the red one. I mean, its color is yellow. Okay, cool. You can see. I'm assuming I got like 22 likes or something. So yeah, so this is an example. Let's say this is a graph, and I label them as these. Like I label the edges as like 1, 2, 3, 4, 5, 6, 7. Using this definition given above, which of bridge edge. Sorry. This definition of bridge edge, that a bridge edge is in an undirected graph is an edge whose removal increases the number of components in the graph by 1. According to you, what edge here will be the bridge edge? Which numbered edge? Oh. Okay, this is weird. Let me try to. We can't see what you're writing with the marker. Okay. And I'm not sure what's happening. You will have to stop sharing slides first, I guess. Only then we can. Okay. Okay. Told you my bad. How do I stop sharing slides? How do I stop sharing? Okay, I should share screen, is it? I guess. Yeah. Okay, fair enough. Yeah, I should share screen. Yeah. Okay. Now, can you see the graph? Still on agenda. Oh, I shared my screen, right? Confused. Not sure what the issue is actually. Only a particular window, please share the entire screen. Yeah, I think I'm sharing the entire screen. It's visible on YouTube. Yeah, like I'm not sure. I think it's a thing that I don't understand of the platform. Just give me a moment. I'm talking with the logistics department. Stop sharing. How do I stop sharing? Full screen slide theme, upload file, eraser shapes. Python I should ask for live file, otherwise I'm just wasting good time. Okay, let's do this test. Can people not see any other screen apart from the current one, even though I'm trying? Can you reshare your screen? I have tried resharing a screen like plenty of times. I'm still not sure what to do. Can only see the first slide. I think on YouTube you can like probably see everything. Okay, so Akhil, I think you're watching this right now. So like right now I have this QuickTime player window opened, and if I scribble something on the tablet, it should show, hopefully. I know it's being shown on the YouTube thing because people are saying that they can see it fine on YouTube. But they are saying they can't see it on Academy, like the current QuickTime player window that I'm inside. It's basically my tablet connected. Yeah, so I'm trying to share my screen on an Academy. It just doesn't work. I click on share screen, I click on entire screen, then I click the button share, and nothing changes. I think if we like I'm not sure. Maybe share and not share and tasking. No, I've selected share and tasking. So basically you can't see anything on the screen, right? Like it's not just the tablet. Even if I switch windows, you won't be able to see anything. Yeah, so the issue is basically not with the tablet per se. It's more like I'm unable to share my screen. Agenda slide is stuck. Yeah, I mean I can move the agenda slide, but that doesn't in YouTube everything's working. Yeah, not sure. I'm asking the logistics department if I can just end class and start it again, and if that might help fix it. Yeah, okay, so Akhil, how do I exit the presentation? Like, I understand I don't want like the okay, delete the presentation. How do I delete it? This is such a terrible experience. Okay, I would just recommend people to like switch over to YouTube for this particular session at least. And like yeah, so what we can do is like can someone share the link here? Hello. Yes, is this Akhil? Hello. Yeah. The slides. How do I delete them? Yeah, how do I delete it? I don't know. So actually on YouTube everything. So yeah. No, I can't. I discussed that with Tanuj. Tanuj told me that like I'm trying to replicate his setup, and I think it would be best. Like I can't write. Okay, hello. So how like okay like can you see my screen right now on any? Okay, so yeah, if I do more and then share screen, I get this window, your entire screen. Then I click share, and then nothing happens. Hmm. What shares? Okay. I don't see how to difference. Yeah, did it. Now can you see the QuickTime player? Okay, can you see the now can you see the scribbling happening? On the YouTube stream, can you see? Yes. Okay. 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 I moved it to another. Yeah. So that's some issue. Yeah. I think normal screen share is not working. Like irrespective of the tablet, like just remove the tablet. I can't just share my screen. That's the issue. As far as I understand, like people are not able to see even other windows if I try to show them. Yeah. Yeah, I'm exit from full screen. Yeah. I don't see any red dot on my thing, on my screen. Yeah, okay, I can scribble. Yeah, I can scribble with my mouse. I don't think so. It's a graph class. It's a graphs class. I have to draw diagrams. Yeah. I see upload file, share screen, slide theme, light mode, full screen. Hmm. Can you see the window right now? Okay. Give it a minute. Can you see it? No. No. No, if I click your entire screen, then I press share, nothing will happen. Okay. Yeah, I clicked on application window. it won't work. I tried like मैं भी CS की डिग्री ले रहा हूँ. क्विक टाइम. तो इसमें इवन क्विक टाइम का देख रहे हो, कुछ आ नहीं रहा है, ग्रे है. इट्स नॉट गिविंग प्रीव्यू ऑल्सो. तो मुझे नहीं पता, मतलब मैं शेयर दबा देता हूँ, बट आई डोंट थिंक. तो वही मुझे पूछना था, अगर एंड क्लास वाला गलती से हो जाता तो क्या सीन है. ठीक है, एक सेकेंड. Okay, I shared the screen again. And how do I like know कि ये screen share हुआ है नहीं हुआ? Not sure. Can you see it now? क्या करें? One thing that I can try out is I have another PC, another MacBook Pro. I can switch on that one. It will just take 2 minutes to transit. Or हाँ, like audience knows कि it's visible on YouTube. Sure, ठीक है. ठीक है, cool. तो मैं YouTube वालों के लिए बोलता हूँ. हाँ, ठीक है. चलो, ओके, थैंक्स, बाय. Okay, sorry guys for wasting like 10-15 minutes. Yeah, we were just switching to YouTube, so don't stay here. Just go to the YouTube link and this is the link. Blah blah blah. Okay, sorry guys. Okay, there shouldn't be any echo. Yeah, probably you can still keep asking questions here. It might be a bit inconvenient, or I'll just try to answer questions from the YouTube stream. Anyways, let's start the lecture. Okay, so we had this thing, right? So can anyone tell me what the bridge will be in this thing? Which edge is a bridge edge? Uh, 3-4 is the bridge edge. Okay. No, so actually the fourth, this edge is the bridge edge. Like this edge, the fourth edge is the bridge edge. Right? Yeah. Cool. And you can create other examples. Basically, whenever you like, if you just remove that a certain edge and the graph disconnects, then you have that edge as a bridge edge. Now, what are articulation points? So an articulation point is a vertex in such a graph which when you remove, the graph breaks. An example will be this. In this graph, let's label these nodes as 1, 2, 3, 4, 5. Can anyone tell me what's the articulation point? And what about this graph? Okay, so I'm starting from the beginning. So we're just discussing what are the definitions of articulation points and bridges. For bridge, the definition of a bridge is that when you remove that edge, the graph disconnects. And for articulation point, the definition is that when you remove that node, the graph disconnects. That's the like easy way to explain it. So in this graph, people are correct. The articulation point is node 3. Why? Because if you destroy node 3, then the graph disconnects, right? This is one component and this is another component. And in this example, when you destroy edge 4, the graph disconnects. This is one component and this is another component. Okay, what about this graph, G2? Articulation points in this graph. So it's not necessary that there will only be a single articulation point. There can be multiple articulation points. Correct. So the articulation points are second, third, and fourth one. All these three. Why is 1 and 5 not an articulation point? Because when you destroy 1, although 1 is removed from the graph, no other thing gets disconnected. Only 1 is removed. So that's why you don't care. And similarly for 5. So only the intermediate nodes you matter to. Cool. So everyone has a broad idea of what the definitions stand for. So what is a biconnected component and what is a bridge component? So simply a biconnected component is a component in which there are no articulation points and it's as big as possible. Okay, when we say as big as possible in like programming or like in a formal algorithms term, people use the word maximal. That is, if you can keep on adding nodes or edges to the graph such that it remains biconnected, that is there is no articulation point in between, then you can keep expanding it. And that's a biconnected component. So in a biconnected component, you will never find an articulation point inside that thing. And what's a bridge component? Similarly, so a biconnected component is a thing which does not have articulation points. You can't find articulation points. Okay, and in a bridge component, you can't find bridges. So maximal does not contain any bridge edge. That's the two important things in the definition. That it's maximal and it does not contain any bridge edge. Now, is this a bridge component? Is this graph a bridge component? Yes or no? Just try to follow the definitions and try to reason why a given graph will be a something. Yes or no? So the answer is no. This is not a bridge component. Why? Because it has this edge as a bridge. If you disconnect this edge, then it disconnects into two components. So it's not a bridge component because it has such an edge. Okay, what do I mean by maximal? By maximal, I mean that it's as big as possible. Let me give you an example. Let's say you have this graph. You technically wouldn't say that this is a bridge component. You will say that the entire thing is a bridge component. You won't just say that these three nodes are a bridge component. You'll say the entire thing is a bridge component. Why? Because the reason is that you can keep on if you can expand it, you should expand it. So that's why it's maximal, that you try to maximize the size of it as much as you can. The size of the structure, the size of the component, bridge component or biconnected component. Okay, poll question. Yeah. So can a bridge component have an articulation point inside it, true or false? Is it possible to create a bridge component such that it has an articulation point inside it? We won't do the actual poll. I think it's like you'll have to just switch windows and it will be annoying. You can just put your answers on the YouTube chat. That is it possible to have a bridge component have articulation points inside it? True. Okay, good. Correct. That's correct. Reason being, example. I'm just giving an example. This graph is a bridge component. Why is it a bridge component? Because you can't find any bridges in it. No matter which edge you delete, it won't break. But it has this articulation point. This node is an articulation point, right? So can a bridge component have an articulation point? Yes. So they're actually like two different concepts. Don't try to mix them. That's the idea. The idea of this question was that don't try to mix them. Now in this lecture, we'll focus on bridges and bridge components. So we won't focus on articulation points and biconnected components. It's more about these two things. How do we find bridges? How do we make bridge components? And why are bridge components useful? Or why is a bridge tree useful? Is the reverse true? No, the reverse is not true. If a certain thing has an articulation point, it may or may not be a bridge component. You can't say that it has to be a bridge component. Okay, everyone understands up to this point? I hope. In case you have questions. So bridge component is edge connected component. Yes, like every bridge component has articulation points. No, not necessary. A bridge component may not have articulation points. For example, like just think of some very connected thing like a clique or something. It won't have an articulation point, and it will be a biconnected component, because even if you delete an edge, nothing will happen. It won't. Yeah, just think of a clique, K5 clique or something. Okay, I hope everything is clear up till now. Now we move on and we check how do we find bridges. So finding bridges, so can anyone first think about what's the slow approach? How do we find bridges? What the question means is, given a graph G, and we want to quickly find all the bridges in the graph, that which all edges are bridges. It's an undirected graph, and we want to find bridges. The slow approach is like almost order E square, and the idea of the approach is pick every edge and remove it and check if the graph has disconnected or not. If it has disconnected, then this edge was a bridge edge, otherwise it was not. It's a simple approach. So just try every edge, remove it, and then like run like a DFS or something, and yeah, BFS will work, and then just tell. So since you have number of edges equal to E, and each edge takes like after removing it takes V plus E times to run the BFS or DFS, so the total complexity is this thing, which is bad. We don't want this slow approach, because for most practical questions you'll have actually V and E pretty big, like order E square won't actually go through. So what's the fast approach? This approach is commonly known as Tarjan's algorithm. I think you originally wrote it for articulation points, but it's used for to find bridges also. And this works in like order V plus E. It's a single DFS. Yeah, so we'll go through this approach. So the idea is root arbitrarily. So just root on some node, just root the graph on some node, run a DFS, and keep track of discovery times in this array, disk array. And you also have another array, low array, and then you do some checking, which is this thing, which is the I think most important part of the algorithm, step D. Okay, the way the algorithm works is, so let's say you have this node as your root. Okay, this is let's say node 1. Now let's say in your DFS you visit node 2, then you visit node 3. Okay, let's not label these nodes, let's label them ABC. So let's say A goes to B goes to C. Now notice what's the discovery time you gave each of them. You gave this discovery time 1, you gave this discovery time 2, you gave this discovery time 3. Okay, now let's say you see an edge C to D, discovery time you gave to node D as 4. Now after C you see another node E in the DFS, you gave it discovery time 5. From 5 you see a back edge. What a back edge means is that you see an edge going to something that has already been visited. Okay, so this edge goes here, it's a back edge. That's why it's known as back, because it's going backwards, more like upwards direction. So because it's a back edge, you know for a fact that the edges in red can't be bridges, right? These red edges can't be bridges once you've seen this back edge, because you know that if I go from C to E and I can go from E to B, even if this edge gets destroyed, they are still not disconnected. Like everything below E will still be connected to B and C through this back edge, because this back edge is actually part of the graph. This back edge is part of the original graph. It's just not part of our DFS tree. Yeah, we cannot say an edge to a parent is a back edge. Yeah, it has to be going somewhere more up. So this is an example of a back edge. So whenever you see a back edge, you know for a fact that some edges cannot be bridges anymore. Okay, that's the idea. Now, so you have discovery times. Now what is low times? So given a node, let's say you're given this node E. Let's say low of E is, okay, so discovery of E is 5. Let's say low of E is also 5. That means there is nothing going back from the subtree of E. However, if low of E was 3, let's say, oh wait, no, sorry, let's say low was 1 here. That meant low is kind of like how much upwards within this subtree of E can I travel. So if low of E was 1, what it meant was that within the subtree of E, there exists some node which goes back to node 1. Why node 1? Because node 1 has the node A, sorry, because node A has the discovery time of 1 and low E is also 1. Do people understand the definition of low? I think that's the tricky part of this algorithm. That low of E is trying to denote in subtree of E which node has the topmost backward edge. Not which node, where does the topmost backward edge goes. Where does the topmost backward edge go to. Low E is in the subtree of E, where does the topmost backward edge goes to. So let's say this edge goes to here, some other edge goes here, some other edge goes here, then what's the topmost backward edge you can take from the subtree of E? That's this one, and it goes way above E. So the condition is basically this: if I have a child whose low is not bigger than my discovery time, then this edge is a bridge. In this example, sorry, the diagram gets ugly quickly because it's a graph lecture. Yeah. In this example, how will you check is if the edge from B to E is a bridge or not? If you have to check whether the edge from B to E is a bridge or not, you will say, let's see the subtree of E. Okay, let's say you calculated low E to be something. Now you will compare this value low E with 2. You will compare these two values. Which two values? Discovery time of B and low E. And if this thing is bigger, if low E is bigger, notice the bigger, greater than sign. If low E is bigger than discovery time of B, that means that whatever you did, you remained inside this subtree. You couldn't get out of this subtree, right? So that means this edge is a bridge edge, because if you remove this edge, this component is completely disjoint, is disconnected from the other component. Whereas on the other example, let's say low E was actually pretty small, like low E could jump till here. Then now even if you remove this edge, they are still connected, right? Can you see why they are connected? Because in the E subtree there is some node here who is going back to B, and everything else is connected. So this edge wasn't a bridge in that case. So the edge from B to E was only a bridge if this condition was satisfied. This is the important condition. I hope everyone understands this. Let me just check the Unacademy thing. Okay. Yeah. Alright. Cool. So, do people understand this? Like, I'm not getting the feedback, so I'm not sure. Why can't there be H to C and D from subtree of E? Good question. Okay. So, the reasoning is like pretty straightforward. Notice it is a DFS tree. It's not a BFS tree or any other sort of tree. Let's say there is this edge to this node, and then this node has an edge to C. Now, if this actually exists, let's say there is a E to F and F to C, this is not possible. Why is this not possible? The diagram that I drew just now, it's not possible because how was your DFS going? Your DFS was at node A, then it went to node B, then it went to node C, then it went to node D, then it came back to node C. Now it should have gone to node F actually, right? Because F is connected to C. Why didn't it go to node F? It should have gone to node F. So once it goes to node F, it comes back up and so on, and then it goes to, and then it sees node E. Okay, actually, when it goes to node F, afterwards it should also go to node E, and so on. So you notice, right, that if there is a node here, it can't go to some other neighbor of it in the DFS tree. It has to go above it. That's a property of the DFS tree that you get. If you're at a node and you're defining a package, the package can only go upwards. It can't go to the left or the right because it's an undirected tree and you're running a DFS on it. Had this been a BFS or something else, you couldn't have said the same thing. Yeah, it might not be applicable for directed graphs, but it is true for undirected graphs that the edges are always upwards. The backward edges, sorry. Okay, so let's go through the code quickly of this thing. It's pretty straightforward. Okay, so I'm assuming everyone can see my screen and the code on it. On the Discord channel, we have also pasted the pastebin code. Which is where? Yep, so here's the code. Okay, and yes, the concept that I'm teaching is only for undirected graphs. Like the entire concept of bridges and articulation points only exists on directed graph. It does not exist on directed graphs. There are variants for it, but this is not the thing. Like the theory will change completely. So you draw, like, let's say you have n nodes and m edges. I'm just going to write comments: n equal nodes, m equal edges, and you get some pairs of edges. Then you add them in your adjacency list. Here I'm creating the adjacency list using a set. This is important to note. It's a set, not a vector. The reason I'll explain later. It's not useful for this part, and that's it. Your DFS bridge code is only up till here. So you call this function DFS bridge. The idea of this function, this is the bridge finding function. You mark each node. Please use dark mode. Oh, is it going to be better in dark mode? Don't think so. Okay, anyways, I can open this on Sublime. I've opened it on Sublime also. Okay, on Sublime I think it's, hopefully it's better. Yeah, so you have adjacency lists and they are sets, not vectors. That's one important thing. Just concentrate only up till this point of code. Okay, don't see like the bottom portion, like just comment it out. Don't bother about it. So what is DFS bridge? DFS bridge is a function which takes in, okay, let's even comment this out. We don't need this right now. We'll need this in the bridge tree implementation. You mark each node visited. You set each node's parents to its previous. You set its discovery time. So that's the disk array. Discovery, disk stands for discovery, as ++ counter. Counter is a global variable starting at 0. You set the low of this as discovery initially. Now you have to now what you have to do is you have to do two things: run the DFS and update the low value correctly. So you loop over the neighbors, auto v neighbor of adjacency. If it's the previous node, just skip it. You don't care if if v is equal to previous. So don't consider the uprev edge. Okay. Otherwise, if it's visited as false, that means this node hasn't been explored. That means it's somewhere below in the DFS tree. So go explore it. That is called DFS bridge on it. And if its low is greater than my discovery time, then this edge is a bridge edge. That is edge from U to V is a bridge edge. Okay, otherwise, okay, and normally just keep on updating your low with the lows that you get. So low u is equal to min of low u comma low v. Like the low definition was kind of recursive in the sense that your low is dependent upon your children's low. Okay, these conditions will satisfy the root of the tree also, because notice the root of the tree. Okay, let me give you an example. Yeah, for articulation points it doesn't work for the root, but for bridges it works. Why? Reason being, let's say your graph looks like this: node 1, node 2, node 3. That's it. That's how your graph looks. Okay, let's add something else also to make it interesting. Node 4. Yeah, let's say this is how your graph looks. Now when you run the DFS from node 1, you check node 2 first. You set its discovery time 1, you set its discovery time 2. You come back, you set this node's discovery time. Okay, now notice when you're going to come back from node 2, you see that the low of node 2 is 2, which is greater than discovery of node 1, which is 1. So this edge becomes a bridge edge. This edge is a bridge edge. Now you see 1 to 3 and 3 to 4, and since 4 has a back edge to 1, there won't be any other bridge edges. So it does work for bridges. If you're trying to do this for articulation points, then you guys are correct. Shobit is correct that you have to take care about like the root being special or not. So this code, if just changed slightly, will work for articulation points. You can Google it up, or later I can share that on the Discord, that if you change this like some of the if conditions, then you can get the thing working for articulation points. Notice in the code one important thing: how are we storing whether an edge is a bridge or not? Using this boolean array, is bridge v equal true. What this boolean array means is that if a node's is bridge is true, that means that node and its parent have a bridge edge. And by parent I mean the parent in the sense of this DFS tree, because in a graph you don't have parents, but in your DFS tree each node has a parent except the root. And if is bridge v is true, that means the edge from v to its parent, that means edge from v to par v. Par denotes the parent, which I put correctly at line 17, right? So this edge is a bridge if the above condition triggers this condition, if low v is greater than discovery. So I'm assuming people understand like how we are storing whether an edge is a bridge or not. Any doubts up till this point, or we can move forward? Okay, let's go ahead. So what is a bridge tree? I'm just worried if there is anything. Is this lecture running? Priyanka, yeah, the lecture is running. In the questions you can see the YouTube link, and you can just go on the YouTube link. Cool. So what is a bridge tree? If each bridge component of a given graph is shrinked into a represented a single node, and these nodes are connected to each other by bridge tree, then the resulting tree forms a bridge tree. Cool. So once you compress all the components, you get bridge tree. Let me give you an example. Let's say you have one component looking like this, then you have another thing looking like this, then you have another thing looking like this. Okay, this is a graph G. How will its bridge tree look like? If this is G, the bridge tree of G, let denoted by B, will look like this fat node connected with the bridge to this fat node, connected with the bridge to this fat node. Okay, basically each bridge component becomes one node. That's the idea. This is a bridge component, this is a bridge component, this is a bridge component. So all of these components become big fat nodes, and to connect two fat nodes there is a edge in between, which is a bridge. In the original graph it was this edge. In the original graph it was this edge, now it's this edge. That's it. That's bridge tree. You basically take all the bridge components, compress them to look like one, like big nodes, and the edges that are left between them are just bridges, so you get the bridge tree. Now, what are the properties of bridge tree? So I think this is the most essential part. So each edge in a normal graph is either a bridge tree edge or part of one of the bridge components. Notice in this graph, let's take an example, this edge. Now this edge goes inside component A. This edge also went inside component A. This edge also went inside component A. However, this edge is a bridge edge, so it remained here, right? So all the edges are either present in components or they are present as bridges. That's it. Like, that's the first property. It's a pretty straightforward property. What's the second property? The bridge tree is a tree. It is not it can't have cycles. That's the important thing. Can't have cycles. So anyone can think why it can't have cycles. Why can't the bridge tree have cycles? Notice again in this graph. Let's say this graph had a cycle. Okay. Let's say, how will the cycle look? It will connect this thing, right? Like right now, this thing is a tree because A is connected to B, B is connected to C. It looks like this. Let's say it was a cycle. Now notice the definition of bridge got broken when we made it a cycle. Why? Because if it's a cycle like this, then this yellow edge is no longer a bridge. Because even if you remove this edge, everything is still connected. So if there was a cycle, then the edges in between, which we were assuming to be bridges, will no longer remain bridges. Exactly. No edge in a cycle can be a bridge. And we already know the way we have constructed this graph is that, yeah, so we have a contradiction, correct? So everyone understands it, that the bridge tree has to be a tree. It can't have cycles. Now, what about the number of bridges in this graph? There can only be at most n bridges. It's pretty straightforward because the bridge tree can only have at most n nodes. So in the original graph, you had n nodes. You compressed some bunch of nodes into fat nodes. How many nodes can you have in the bridge tree? At most n, right? And it's a tree, you know, or it's a forest of trees. Either way, even if it's a tree or it's a forest of trees, the number of edges it can have is less than n. More precisely, at most n minus 1. The number of edges that bridge tree will have. And each of the edges will be a bridge. So the number of bridges is at most n. So these are like, you should remember, whenever you think of bridge tree, you should remember that like you get all these properties for free if you are creating the bridge tree. So these are the easier properties, I would say. We did the proof right now only. So first poll, like we have 2 poll questions. I think both are interesting. First one is, within a bridge component, if I pick any pair of nodes u, v, will there always be a simple cycle crossing between them, crossing both of them? Example, let's say this is a bridge component. Okay, label the nodes 1, 2, 3, 4, 5. If I pick any pair of nodes in this component, let's say I pick 1 and 3, do they have a simple cycle going through them? For 1 and 3, yes. You can go from 1 to 3, 3 to 2, and 2 to 1. This is a simple cycle. Going from 1 to 3. Going from both 1 and 3. If I pick any other pair also, you'll get. Does this hold for every bridge component? This is just one example of a bridge component. Will this hold for all bridge components? Yeah, so some people got it. I think it's quite hard to actually be like, you can have an intuition for it. I think proving it is like relatively hard. Yeah, but true is the answer. We'll prove it later on. Second part, if you have a 8-shaped graph, how will what does a simple cycle mean? Okay, so a simple cycle basically means you don't go through a vertex twice. No, you can't repeat vertices. That's it. That's the definition of simple cycle. You can't repeat vertices. Okay, the bridge tree of a shape 8 graph, how will it look like? So shape 8 graph will be something like this. Let's say this is your shape 8 graph. If you have this graph, how will the bridge tree look like? Let's label them A, B, C, D. You can tell me what you think. I just want to have these polls so that people have a more better understanding of what's a bridge tree. So if you have this shape 8 graph and you try to create a bridge tree out of this, How will you find a cycle for 1 and 4? Good question. Okay, my bad. 1 and 4, 1, 2, 3, 5, 4, 3, 1. Yeah, you're right. I think I missed out something. This is a bridge component. Okay, it's actually edge disjoint then. Yeah, it's edge disjoint. My bad. So the cycle is actually edge disjoint. It's not vertex disjoint. Edge disjoint you can see easily. 1 to 3, 3 to 4, 4 to 5, 5 to 3, 3 to 2, 2 to 1. This cycle is edge disjoint. You don't repeat edges. Yeah, my bad. Vertices can repeat. Correct. Okay, what about the second question? Can anyone think? Yeah. The bridge tree of a shaped graph will look like how? For this graph, how will it look like? 1, 2, 3, 5, 4, 1. Okay, that won't work. Yeah, you can't go from 4 to 1 directly. Anyways, I think Samarth is right that you should be allowed to repeat vertices. You can't repeat edges. That's the condition. Yeah. For this one, anyone has any idea how will it look like? Will it be a 2-node connected component by an edge, the same graph, a single node, the same shape graph without an edge? Correct. Yeah, that's the question. Yeah, there are no. So the answer is actually a single node because there are no bridges. You try to disconnect any edge, you still be connected. So the entire thing is just one big component. So when it gets compressed, it will just be compressed to a single node. That's it. Okay, so now you have these two more properties. First one is, within a bridge, there is at least one way to orient all the edges such that there is a simple path from any node to any node within the component. Okay, what this means is, initially in the bridge component, all the edges are undirected, right? If you want to direct them in some direction, like in one of the directions, like let's say there is an edge from U to V. Now you want to direct it to say that it should go from U to V, or you want to say that let's change the direction to this. Either way, if you want to do it, within that bridge component, there must be a way to orient all the edges such that you can take any node and go to any other node. Yeah, Samarth, I honestly don't know how it will work. And I don't want to waste people's time on this YouTube thingy right now. I mean, for the next lecture, definitely we'll do something about it. Hopefully we'll get the unacademy thing fixed. So within a bridge component, there is at least one way to orient all the edges, such that there is a simple path from any node to any other node within the component. Yeah. What's the proof? The proof is relatively, I would say, not that straightforward. The idea of the proof is you take a node. Now what you do is you run a DFS from it. In that, so I'm talking about a bridge component. Let's say the bridge component is G. How will I direct its edges? I'll take a node, I'll run a DFS from it. And in my DFS, I'll just keep on assigning the direction to go downwards. Okay. Now, whenever I find a back edge, let's say I found this back edges will be in up direction. So normal edges will go down, back edges will go up in my DFS tree. Okay, when I'm doing that tree, I'm just showing you how to get the orientation. So you'll do this, and then let's say you have some other DFS tree also. Let's say you're going here, you're going here, you're going here, then you go here. Okay, and let's say maybe you started from here and you eventually go here also. Give me an example of 4. What do you mean by example of 4? 4 things, I'm not sure. Okay, example of 4. Okay, point 4. If you have, let's say, this graph, it doesn't have any bridges, right? And you can orient all the edges such that Okay, I mean this one is a cycle, so it's pretty stupid. Yeah, now in this graph there were no directions, but you could change, you could add directions to each of the edge. In this graph you have the property, no matter which pair of nodes you pick, you can travel from any node to any other node. Yeah, you can orient it to an SSE, correct. Like, I don't want to use the term SCC because some people might not be familiar with it, but that's the idea. You want it to look like a SCC. SCC stands for strongly connected component. You don't need to know it, like you can Google it up later on if you want to. But anyways, so this is the thing. So how do you do this construction? You run a DFS from the top, keep on orienting the edges as you go down, and whenever you take an upward edge, you give the direction up. So this edge is given the direction up, this edge is given the direction up, and so on. And the reason this works is, if you're at any node, let's say you're at this node and you want to go somewhere down, you can easily take the downwards edges, right? And if you're at any node and you want to go up, okay, then you take some down nodes and you reach some back edge and climb that back edge, and try to go up that way. This is not an correct example, I would say this is more like a correct example, but yeah. Can't we just orient along the simple cycle? Finding the simple cycle is harder, Rishabh. You can't just find simple cycles. And like, how many simple cycles? Like, a bridge component can have many simple cycles. It's not necessary that it's only one simple cycle. I just created small bridge components so that it looks like it's a one simple cycle. But there can be many. So that's the idea, that if you're at any node and you want to go down, you can just take the path going down. And if you're at any node and you want to go up, you go down slightly, take a backward edge to go up. Like, basically, kind of the idea is that you have to short circuit, like go down a bit, take the upward edge going from there, and then go down a bit. For example, let's say you started at this node, okay, and your aim was to reach this node. Now you'll go here, you'll take this backward edge, then you'll take this backward edge, and then you'll come down. But you were able to do that. Yeah, this graph still has bridges, correct. I mean, I didn't create this graph carefully. Probably now it doesn't. Yeah, I don't think it does have bridges anymore. But you were right, it earlier had bridges. And basically you can do this upward climbing because there are no bridges. So you know for a fact there has to be some upward guy going. Where if you're at any place in this DFS tree, and you will definitely be able to find a way from downwards so that you can take up back edges. You'll find those back edges because there are no bridges. That's why the thing works. Are people clear with this? Property 4. Okay, let's move on to property 5 then. Within a bridge component, for any pair of nodes, there must be a simple cycle between these two nodes, as we defined earlier. You need to show that starting at any node, you can climb to the root. Correct, Samarth. Can we do something like the algorithm for finding an order 2 and decomposing that component and cycles and then making them? You can probably. I think this will work, but I think it will be tedious to code. This is probably much simpler. But I think something like that should work. Okay, so what's the fifth property? That within a bridge component, if you pick any pair of nodes, there must be a simple cycle between these two nodes. And yeah, the simple cycle definition has been changed. It's edge disjoint now. The reason is, let's say there is this node U. Within the bridge component, let's say you find this node V which you wanted to find. Okay. Now you start going from node V, and you just go, and you reach here. Okay. And if you are able to find a path back to U, you are done. Your proof goes through. Correct. So when does your proof not go through? Your proof doesn't go through when this thing hits somewhere here, somewhere on the path, right? And obviously after some finite amount of time, it has to hit some node that you already have seen. Let's say on this path you had some nodes. after some finite amount of time, it has to hit some node on this path, right? Now, if all the paths from V look like this, and none of them actually go to U, but they all go to like some other place, okay? Like there are nodes in between, I'm just not drawing them. This is not possible in a bridge component. Why? Because if this was possible, that means this edge would have been a bridge edge. This edge would have been a bridge edge, which is a contradiction. So if you're able to go from U to V, you should definitely be able to come back also. Do people get this point? That if you're able to go from U to V, you should be able to come back. You can't just, like, all the paths can't just stop somewhere in the middle. Because if all the paths are stopping somewhere in the middle, then this edge from U to U1 will become a bridge, which is a contradiction. You can't have bridges. So there must be a path which goes back. It might be sharing some edges, but there must be a path going back. That is quite lag in the chat. Okay, now how do we make the bridge tree fast? That's the next point. I'll slightly rush through this right now. So the way you do it is, you first run the bridge finding algorithm, find all the bridges basically. Now remove the bridges from the graph. So let's say your graph looked like something like this. This was your graph. Let's say the red edges were bridges, okay, and the black edges were normal. Now what you'll do is, you first find all these bridges, so you color them red. Now you remove them. Once you've removed them, the edges, you're left with small components, right? So in the resulting graph, the nodes in two different bridge components now look disjoint, correct? And just label all these nodes with their component ID. What this means is, start a DFS from this guy and label all these nodes 1, 1, 1, 1, 1. So basically this entire component is node 1. Label all these nodes 2, 2, 2, 2. This entire component is node 2. Label all these nodes 3, 3, 3. This entire component is 3. Label all these nodes 4, 4, 4. This entire component is 4. So you have 1 component, 2 component, 3 component, 4 component. Now add the bridges back. So there was a bridge here, right? And there was a bridge here, and there was a bridge here, and there was a bridge. No, I think there was a bridge here. That's it. Yeah. So you add this edge, this edge, this edge, and you get your bridge tree. So the idea is pretty simple. You take the original graph, find the bridges, remove the bridges, then just compress each thing into small nodes and add the bridges back. That's what this like pseudocode algo is. Let the total number of nodes in these components be k. Now add back the bridges, and the new graph you get has k nodes and the bridges as your edges, and this entire thing is your bridge tree. Fair enough. And what's the complexity of this thing? So this step was order v plus e. This step was order e. This step is also order v plus e. So if you do it, and like you can check all the other steps are also pretty fast. If you do it pretty fast, then you'll get order v plus e. The implementation that I'm going to show you will be v plus e times log e. It will have this additional log. It simplifies the implementation slightly because I use sets. But it's not necessary. I mean, you can have faster implementation if you want to. It's just that order e log e generally for practical purposes will not time limit or anything on a comparative programming problem. So you don't have issues. You can do it, most likely. Okay, moving on to the implementation detail. So now I'll just uncomment the parts that I commented earlier. This is the part. This is the code of the bridge bridge tree. So after finding the bridges, I create this vector named bridges, which is going to store all the bridges, right? And it has pairs. Each pair is of the form node 1 comma node 2, which are the two endpoints of a bridge. So I just go through all the nodes. If it's a bridge node, that means I in the DFS traversal was a bridge node. That means edge from I to pair I is a bridge. So if it's a bridge node, you add it. So bridge dot pushback, sorry, bridge edge. It's a bridge edge, and the edge is between I and pair I, right? Pair I basically denotes parent of I in the DFS tree. So you add this edge in your bridges list because this is a bridge, and you remove these two edges in your adjacency list. You're removing the bridge from the graph. So removing bridge from the graph. That's why I use the set set. Instead of a vector, I use set because this is just easier to code, because you just call erase and that's it, you're done. You've erased the neighbor. In a vector, you would have iterated on it, manually removed it, concatenated back. It would have been more implementation detail. Sure, I'll share the PPT with the drawings after, on Discord. So adjacency I, you erase the parent I, and from parent I you erase that. Basically you remove this bridge from the graph, and that's it. You do this for all the nodes, for all the edges which are bridges. So line 58 controls for which edges you do this. Okay. Now once you've removed all the bridges, you have to label them correctly. So what you do is, if a node is not visited, you label it. And what do you label it with? You label it with counter variable. So initially counter becomes 1, and label is just a flood fill, and it just sets the label of each value to the counter. This line is important, line 35. It just sets each of the value, like the label of that component, to 1, all of them to be 1. Then in the next component all of them get set to 2. Then in the next component all of them get set to 3, and so on. That's it. So DFS label just colors, or you can say label, the different components that are now formed. Make sense? That what we are doing here? We are just labeling the components. The reason why we are labeling the components is because each node now has an identity associated with its component. Now bridges are not between nodes, they are between components. They are between bridge components, right? The bridges are edges in between components. They are not between nodes anymore. So you add them back. So what you do is, you iterate over the bridges for auto V bridges, take the label of the left point, take the label of the right point, and add an edge between those two. So A is basically the label of the left point, V dot first, the left node of the edge of the bridge. B is the right node, and you take their labels. So V dot first is the left edge, left node, V dot second is the right node. You take their labels, you get A and B variable. So these are the component IDs. A is the left component ID, B is the right component ID. And you say both of these components are now connected with an edge in your bridge tree. So your bridge tree is denoted by B. And that's it. Your bridge tree is created. So notice how your bridge tree looks. It's a for each node you have an adjacency list of the neighbors, and it's a tree. It's how, like, in standard implementations you implement a tree to look like. Clear on line 57. Oh yeah. I do clear, yeah. I just, so those are like slightly unnecessary things. I didn't bother to explain them. If you've done some graph questions, you know that we have to clear visited arrays and everything else. But yeah, so the construction of bridge tree is pretty straightforward. And the complexity, the reason it came out to be E log E was because of this arrays, right? And this insert, because sets are slow in insertions and deletions. And even when you're iterating, here you're iterating on a set, not on a vector. Notice So this is also slightly slow. So you have log factors here and there, but for practical purposes it won't matter. And you can, like as a homework problem, if you want to, you can implement this without using sets, just using vectors. Okay, so moving on, we have, I think we had 4 problems to discuss. We'll probably discuss, I think, like 3 problems, maybe skip one of them. I think so, because I don't know, we'll have enough time. So first problem is this one. Given an undirected graph with n nodes and m edges, you can add at most one edge in the graph between any 2 nodes. Find the minimum number of bridges in the resulting graph. Any ideas? Notice we have just learned about bridge trees and how we implement them and everything. Try to think about it from the context of articulation points, bridges, bridge trees, and stuff like that. Just think about it for a minute. Like, let's give this problem. Correct. Yeah. So Dhruv and Aryan, both of them got it. Yeah. So you basically draw the bridge tree. So the question's objective is you have to minimize the number of bridges in the resulting graph, right? So let's say in the original graph, the bridge tree of the original graph, let's say it looks like this. Now after having drawn the bridge tree, you're thinking about adding an edge, right? Now let's say if your edge is within this component, let's say this is component A, B, C, D, F, G, H, I. If the edge you're adding U, V, if U is in C and V is also in C, if they are in the same component, then that edge is useless for you. Because if they are in the same component, they don't help you in any way. They don't destroy any bridges, right? But if let's say you draw an edge between F and G, then you created this cycle, right? So you destroyed these 2 red edges, bridges, kind of like these 2 bridges no longer remain. You were able to remove 2 bridges from the graph, because if you draw an edge between F and G, what it means is you pick a node U in F and you pick a node V in G and you add an edge between them so that F and G are now connected. Now the benefit you got was that you were able to destroy 2 bridges. The question is actually asking you to destroy as many bridges as you can, because you want to minimize the number of bridges remaining. So instead of adding between F and G, you could have added between any other 2 nodes also, right? And so if you add an edge between B and I, let's say, then which all bridges will you destroy? You'll destroy this bridge, this bridge, this bridge, this bridge. So 1, 2, 3, 4. You'll destroy 4 bridges. So basically the number of edges on the path from between those 2 nodes, that's the number of bridges that you'll destroy. So now you can easily see that to maximize this, you should just pick the diameter, because the diameter, what's the definition of a diameter of a tree? The definition is that it's the farthest 2 endpoints in the tree, right? So it has the maximum number of edges on the path. So in this case, the diameter is probably from I to D. So if you add an edge from D to I, then you'll destroy this, 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 this. You'll destroy 5 bridges. And so in the resulting graph, the number of bridges remaining will be just this one and this one. Okay, and this one also, sorry. Okay, pretty straightforward. Cool. Okay, so second problem is no longer valid because I thought that the property was actually vertex destroyed. Yeah, I was mistaken. So just skip this problem for now. This is actually a problem for biconnected components, if I'm not wrong. For this problem, hard problem 1, what's the question? So given an undirected graph and queries of the form UI, VI. So you're given multiple queries. I goes from 1 to n. Okay. And can you orient all the edges such that there is a path from UI to VI for all I? So meaning, yeah, Samach, you're correct. After adding the edge, the nodes of this on the cycle can be merged into a bridge component. So all those edges on that path, which were earlier bridges, are no longer bridges. You can think about how the new bridge tree will look like, but you don't really care for that particular question. You just know that all those edges won't remain bridges, and you won't add any new bridge also. So the calculation is simple. Okay, so for this one, what's the question? You're given some queries. So let's say there's this query U1 to V1, there's a query U2 to V2, and there is a query, let's say U3 to V3. Let's say you have 3 queries. What it means is, you want to no, Keshav, that's the definition of a Hamiltonian cycle, and you can't say you have a Hamiltonian cycle. Yeah, because what you're trying to say is that it's a simple cycle, so that means every vertex is covered at most once, and because it goes through all the nodes, at least every vertex is also visited. So you're basically saying that it has a Hamiltonian cycle. I don't think that's true for bridge components. Otherwise, like, because I think a Hamiltonian path problem is like Hamiltonian cycle is a NP complete problem. Yeah. So you won't find a polynomial time solution for that. Anyways, so let's say you have this U1, so the 3 queries are U1 goes to V1, U2 goes to V2, U3 goes to V3. Now you want to orient the edges in your graph, which is currently an undirected graph, such that all these 3 are satisfied. That is, there is a path from U1 to V1, there is a path from U2 to V2, there is a path from U3 to V3. So to do that, first think about the bridge tree. You can easily see if U1 is here, V1 is here, U2 is here, V2 is here, then the answer is no. You can't do. Why? If U1 is here, this edge has to be going up, this edge has to be going up, this edge has to be going down, this edge has to be going down. For the path from U1 to V1 to be valid. Now, once you have the path from U1 to V1 valid, now you want to make the path from U2 to V2 valid, right? But notice, from U2 to V2, you go from here, U2 up, and then this is a contradiction. Right? So you can think about that you'll get these sort of contradictions. And what happens if, so this is one case. The other case is, what if inside this component, let's say zoomed in, this component looks like this. There is a node U1 here, there is a node V1 here, there is a node U2 here, there is a node V2 here. Can you orient them in such a way that there is a path from U1 to V1 and there is a path from U2 to V2? Within a bridge component, can you do this orientation? Well, you can, because of property 4. That's why we did property 4. That was the reason I showed property 4. Property 4 just said this, that within a bridge component, you can orient all the edges in such a way that for any pair of nodes, you can go from one node to the other node. So, if there are queries within the component, then we can always orient them. And if there are queries across components, that is, one node is somewhere here and the other node is somewhere at another place, then the problem is tricky, but we at least know now that we have to solve the problem on a tree, not a graph. Because it's now no longer a graph now, it's a bridge tree, it's a tree. So the original problem now changed to solving the problem on a tree, which is relatively much simpler than the original problem. So the reason you would do this, how you would do this is, I can give one example implementation which works. If you have, okay, let's draw a generic tree. So if you have this U1, V1, you'll just find the LCA. I hope everyone knows what LCA is. lowest common ancestor, you'll basically, what you want to do is kind of force all the edges from U1 to LCA to go up and all the edges from LCA to V1 to go down. You want to force these two conditions, right? And you want to do this for all pairs from U1 to V1, then U2 to V2, then U3 to V3. Take their LCAs and force these conditions. And if any edge gets a contradiction, that is, it wants to go up also and down also, then the answer is no, otherwise the answer is yes. So you can think about how you'll do it fast. One way to do it fast, that is in order V plus E, is to create two arrays up and down. When you have, let's say, U1, V1, what you do is you set up of this thing to be 1. You increment the up here and you decrement the up here. You increment the down here and you decrement the down here. On this node, you decrement both the up and down. Here you increment the up, here you decrement the down. The idea is, when you will be running your DFS or something, you'll check what's the sum of ups in the subtree and sum of downs in the subtree. Okay, if the sum of ups is greater than 0, that means the children below me are saying me that I should go, that my edge to my parent should be in the upward direction. And if the sum of downs is greater than 0, this should be more clear. Sum of ups is greater than 0 implies that this edge should be upwards, like this. If sum of down is greater than 0, it implies this should be downwards. So if both of them are true, answer is no. Otherwise you can just keep doing this. You can think about why will this work, this up and down trick. The idea is that you did a plus plus here and you did a minus minus here, so you're kind of cancelling the effect. That when you reach the LCA, beyond that point, above LCA, nothing will be affected by these two, U1 and its LCA, they won't affect. But on the path from U1 to LCA, there will be this, they will affect the up array. So you're kind of adding a +1 on this path. On this path, you added a +1 in the up array. And on this path, you added a +1 on the down array. And for every node, you'll check if the up array and the down array both are positive at that point. Then it's a contradiction, because both of them are saying to go in opposite directions. So that's it. Right? It has a code forces problem link. You can try to attempt it if you want to. I think it's some dev1 or something. It's quite hard, because I think the idea of bridge tree was relatively new at that time. So this is the last problem. Yeah, then we'll end the session. Given an undirected graph G is equal to VE with cost associated to each edge, find the best way to remove a bridge edge and then add a new edge such that the graph still remains connected and the sum of edge weights is maximized. I have added the CodeChef problem link. It's some external contest. The problem is relative. I think it's quite good. The constraint on V is 1000. So something like n square log n will work. Okay, notice that this will work. So you want to find a way to remove a bridge edge. So basically you have this matrix weight UV for all U for all V. That is, for any pair of nodes, you have this matrix well defined. Okay, that is, if you add this edge, how much will it profit you? Or if you remove this edge, how much is it costing you? So let's say you have an original graph. And let's say there are some bridges. Let's denote them by red. Yeah. And yeah, so you thought of a way to remove, you have to basically remove a bridge edge and then add a new edge in such that the graph still remains connected. So since the question asks about bridge edges, so you should quickly think about bridge tree. Now what is happening in the bridge tree? The question is basically saying that remove one of the edges of the bridge tree. Okay. And instead of that edge, add another edge in the whole graph. such that the graph is still connected. So let's say we remove this edge. Then if we remove this edge, the new edge that we'll add, if it's from component A to component B, component A must belong to this portion. Okay, and component B, let me do this another color, must belong to this portion. These are the two disjoint portions, right? So you should pick a node from this portion and a node from this portion and add an edge between them. That's what you want to do. And you want to do it in such a way that the weight of this thing is maximized. Out of all the options, you want to pick that option which maximizes the weight. Right? So, what's the slow solution you can think of? Take every edge of the bridge tree, remove it. So I just removed this edge. Then iterate over this n square matrix of weights and check if this component lies in the green part and this component lies in the red part. If that's true, then you can say that this is a possible candidate, weight UV, and pick the best candidate possible, the maximum candidate possible. So let's say all the edges had weights. So this was weight 1, weight 2, weight 3, weight 4, and so on. So from your total answer, you subtracted weight 3 and you added max of weight u comma v, where u belongs to component A, that is the red component, and v belongs to component B, that is the green component. Right? That's the slow solution. I'm just explaining the slow solution. The slow solution is actually order n cube, because the number of edges that you'll have in your bridge tree is order n, and for each edge you do this max, which is order n square, overall pairs u comma v, and you check these two conditions also. You can check these conditions in O1 if you're smart about it. So you have order n cube right now. You can think about how you'll make it in square log n instead of order n cube. The optimization has to do more with trees and graph theory than bridges. You already exploited the concept of bridge tree when you made this tree and said that we'll remove this. So this thing, instead of n square, should be made order n log n using a set or something. You can think about it as a homework. It's not really related to the content of this lecture. And once you make it n log n, your net complexity will become n square log n. So you'll still try to remove each edge, but whenever you remove an edge, you should have a reasonably fast method to find this best candidate, this thing. And once you find the best candidate, that's it. You just keep on trying for all the edges possible. So your final answer will be max of total minus weight I plus summation u in A, v in B, max of weight u v, u in A, v in B, and I is one of the bridges in bridge tree. Right? That's how roughly the entire algorithm looks like. And you have to speed up this part to become n log n instead of n square, that you can think about. So that's it for this lecture. You can read up Tanuj's blog post or his lecture video for more explanation, and for other example questions. He also covered some Biconnectivity component details. So bridge tree was a way to compress bridges. That is when bridges are important to you. If articulation points are important to you, people generally use block cut trees. This is another data structure that exists. We did not try to cover it in this lecture because it's relatively more complex and generally useless, like less used or less occurring, but it is more powerful. So it is more powerful, like that's a fact. It will be more powerful than bridge tree. Any question that you can do with a bridge tree, you can pretty much do it with the block cut tree also. But it's harder to code and it's slightly less intuitive. And you will definitely see that it's harder to code. Like I've tried to code it I think I've coded like twice or thrice, and it's like it's quite a pain. Whereas bridge tree is generally easier to code, because if you know just how to find bridges, you're pretty much done. You just remove the bridges, make the components, and then add the bridges back. That's it. So that's it from my end. If you have any questions about any of the intermediate topics that we covered, then let me know. Yeah. And I would say, like, the easiest way to see applications of such things is notice the wording on the problem. Like, sometimes in the wording of the problem, you'll see that if you destroy this city, that the electricity is disrupted overall. Like, try to find try to practice some questions on articulation points of bridges, and you'll notice that how is the question generally framed when they want to signal you that we are talking about bridges, or we are talking about articulation points. Because once you see that the problem requires you to find bridges, or problem requires you to find articulation points or something, then it should be a natural thought for you to consider bridge tree also as a problem solving technique for that question. Yes, Snigdh Sinha. Yeah, you're correct. For the n-square pair of vertices, we try to remove the edge of the min weight on the bridge tree between them. So you're removing, actually, you're trying to remove every edge of the bridge tree. The thing that you're trying to add is considering all n-square pairs. The edge that you're removing is just every bridge. You try to remove every bridge each time, and when you remove the bridge and you're trying to add an edge back, to add the edge back, the naive way is to just consider all n-square pairs, and you can optimize it to make it n log n. Yeah. So, like, I'll just wait for like another, I think, 3 to 4 minutes to answer any of the questions that people have. And it's not really a path query algorithm, it's actually very simple. Like, for this last question, it's like you maintain some sort of set and just try to query the max element of that set and update that set. It's more like maintaining a balanced binary search tree. You just maintain the set of pairs of elements green cross red, and whenever you change positions in your DFS, you just change the state just slightly. You can think about it. It's not really essential to this problem. Alright, I think we are done with the lecture then. Oh, Anmol, I'm not sure. I don't have any idea. Yeah. Okay, I think we don't have any doubts. That's cool. So I'll try to upload this and like make some rectifications about the vertex cover thingy that was slightly incorrect. Just ignore that part, because I think it's related more to backnetted components than this. I think all the other part, yeah, you can just take it for face value that it's correct. Cool. Thanks a lot for coming, and I hope to see you guys tomorrow also.